In this lecture, we'll be covering part of Chapter 14, which is going to be over the immune system and the lymphoid organs. So the immune system in your body is going to be what provides defense against any sort of infectious agents, all the way from viruses, all the way up to multicellular parasites. Now, this defense that they're providing is, in other words, the immunity that you have against foreign organisms. Now, there are two overlapping lines of defenses that are going to assist in providing defense against anything that's abnormal or potentially harmful. The first is going to be the innate immunity, and this is the first one that's going to be present in your defense. It's going to be quite a bit of things that are going to be in play here, which we'll learn a lot more in the other course, immunology. Generally, this type of immunity is considered older, evolutionarily speaking, than adaptive immunity. It's more primitive if you want to think of it that way. And most of the cells that are going to be involved in this are your granulocytes and a few other leukocytes. So the other one is adaptive immunity. This is going to be aiming primarily at specific invaders. And the way this is going to be done is through our lymphocytes. If you remember from last chapter, are your T cells and B cells, and another group of cells called antigen presenting cells. From here on out, we're going to mainly consider these APCs. Now, what adaptive immunity does is it provides your cells with what we call a memory of what you've been exposed to, so that if you get exposed to the same thing again, it's going to provide a much quicker response to that foreign invader. So most of your lymphocytes are going to initially start in primary lymphoid organs. Now this is going to be your thymus and your bone marrow. And remember last chapter we covered the bone marrow a little bit more in depth. This chapter we're going to focus on the thymus. The lymphocyte activation and the eventual proliferation is going to occur in what we call secondary lymphoid organs. Now these are going to be your lymph nodes, your tonsils, and so on. And there's also another group called the mucosal associated lymphoid tissue, which is your MALT. And this is another group of cells that are going to be involved in the immune system. Now, if you think of it, your mucosa is your barrier to the outside world. So think of your nasal passages in your GI tract. This is where a lot of different exposure occurs. So this is where a lot of our lymphocytes are going to be found. Now, whenever we have proliferation in the MALT, it's going to primarily be in the small spherical lymphoid nodules. So here's the overall body with all the different lymphatic or lymphoid organs. Of course, this is the one that we're going to focus on in this chapter, the thymus. We covered the bone marrow last time, and the secondary structures are going to be right here. So the innate immunity is what we're going to go over first because it's more primitive and a little bit easier to understand. It's going to mainly be involved in immediate non-specific actions. So think for a second whenever you get a sore throat. Generally what this isn't due to the microbial infection or your respiratory infection, but rather it's due to your leukocytes having very non-specific actions. So what's going on is your cells don't care what's going on. What anything is, it's going to kill everything it sees in hopes of killing the invader as well. Now, the innate immunity doesn't just include your leukocytes and granulocytes, but rather it also includes physical barriers, which this will be your skin, mucosa, anything that prevents foreign bodies from entering your body. Now, once they do enter your body, if they do, the neutrophils and your other leukocytes are going to very quickly remove anything that's there to prevent any further infection. Now, the way that your cells are able to identify things that are not yours is through what we call toll-like receptors. These are on your leukocytes, and they allow the recognition and binding of anything that's foreign. Now, there's another group of cells called natural killer cells. These are going to destroy anything that's unhealthy, that's your own cells. Now, if your cells get infected with a bacteria or virus that actually goes inside the cell, it's going to allow the natural killer cells to come by and go, hey, this guy's sick, let's just go ahead and kill him and get a new one in its place. Now, another interesting thing about the natural killer cells is it also works with tumorigenic cells. So if you get a tumor, your natural killer cells, or cancer, is going to come in and try to get rid of it as well. Now, the way that they are going to do their defense is based on various chemicals that they're able to release. Now, the first one is, of course, hydrochloric acid and organic acids. So what this does is it's going to lower the pH of the area to either cause the foreign invaders to die or just in general inhibit their growth. So hydrochloric acid, if you want to think of it like this, can either be cidal, and if it's a bacteria, it'll be bactericidal, which means it's going to kill the foreign invader, or it can be static. So if it's bacteria, it'd be bacteriostatic, where it's going to just prevent their growth and keep them at the same number so that they're not overrunning everything. The next one is defensins. These are short cationic polypeptides, so they're a protein. They're produced by neutrophils and a few other epithelial cells that are in your innate immune system. And what they do is they kill bacteria. So these are going to be cidal, and they are going to by disrupting the cell wall. So if you can disrupt the cell wall, things start leaking out and the cell eventually dies. They also release lysozyme, which is another enzyme made by neutrophils, and this is also going to get rid of the bacterial cell wall. Complement is very large in your innate immune system, and it's just a bunch of different proteins. If you remember from when we were covering blood, it's one of the components of plasma, and it's going to react with bacterial surface, or with the bacterial surface components, and this will assist in getting rid of the bacteria through your other leukocytes. And then we have interferons. These are paracrine factors, so if you remember, this is going to affect cells that are locally to where it's being released, and they're going to be released from leukocytes as well as virus-infected cells. Now, if your cells get infected with a virus, they're going to release these interferons to assist in removing the cells that are infected before they can release a bunch of new viruses. And what this does is actually signals NK cells to kill these cells and anything close to them to help resist any more infection. So that's the innate immune system response. Now we're going to go into the more complex adaptive response. Now this is kind of acquired over time through exposure to microorganisms. So you don't automatically have an adaptive response to everything. These are going to be things that if you're exposed to the common cold, a certain strain of it, you'll be resistant to that strain for the rest of your time. However, that virus tends to undergo mutations quite quickly, so that's why you're able to get the common cold multiple times, is because it's not the same strain that you received previously. Same with the flu. You get a vaccine every year. This is to assist with your adaptive response to it, so you won't get that specific strain that year, but the virus will mutate, and next year you have to get it again. Now, adaptive response is acquired through the exposure, and it's more specific than the innate immunity. It's much more slower to respond, and is evolutionarily more recent than the innate. This is going to involve your B cells and T cells, or B lymphocytes and T lymphocytes. Once they become activated against a specific invader, they are going to begin proliferating and mount a defense against that invader. Now, the way they are able to become activated is by what we call those APCs, those antigen-presenting cells. They're going to go to those lymphocytes and say, look what I found, do you recognize this? If they recognize it, they're going to become activated, proliferate, and eventually start their defense. Now, most of your APCs are going to come from monocytes. Now, this is a very specific immunity, and once you have a defense against it, they will stay around as memory lymphocytes, so that another response can occur much quickly against it if you ever get exposed again. So when you get your flu shot, you're doing a memory lymphocytes to that exact flu virus. You have a little bit of a reaction when they inject it, but it's not enough to cause you to get sick normally. And this will allow your body to recognize it if you ever get exposed to it. So, cytokines are part of your immune system, and they are going to be kind of how your immune system communicates with each other to coordinate any sort of defensive measure. So, cytokines are found in both your innate immunity and your adaptive immunity. And they tend to be very low molecular mass glycoproteins. So remember, glyco is for sugar. Proteins, of course, is a protein. So this is a sugar protein, and it's going to have a paracrine mode of action, which means it's only going to affect the cells nearby. Now, what occurs whenever cytokines are released is either chemotaxis. This is going to be causing the cell to come towards that area to assist in the defense. So if there's a lot of inflammation in one area, this is what's being caused, and these are called chemokines. They'll also increase mitotic activity in certain leukocytes, both locally and in the bone marrow. So if you remember last time I was talking about how the bone marrow is able to respond to the needs of the body to produce leukocytes, this is how it occurs. It also is involved in stimulation or suppression of leukocyte activities in the adaptive immunity. We call these interleukins. And the last way is it actually stimulates phagocytosis or directed cell killing by the innate immune system. So, probably the most important part, and you must know this because if you take immunology, I need y'all to know this so that I can tell Dr. Newman that I covered it and y'all know what an antibody is. This is very important. We've covered it once before, but we're going to go more in depth now. So, antigens are the molecule that's recognized by the cells in the adaptive immune system. So these are just some sort of molecule that's going to be recognized by cells and elicit a response from these cells. Now, immune cells will recognize two small areas of that molecule of the antigen, and we call these epitopes. So if we have a very large protein, this whole line is one protein. So you see how it kind of covers up and is a 3D structure. An epitope may only be a small portion of this. So the epitope may just be this one part right there. So your response to antigens are going to either be cellular, which is going to be lymphocytes that are going to get rid of the antigen, humoral, which is antibodies, are going to get rid of it, or it can be kind of a mixture of both. In most cases, it's going to be both to get rid of it, because that's the most effective way to get rid of a foreign antigen. So antibodies are glycoproteins. So again, they're going to be primarily protein with some sugar bound to the protein. They're part of a very large family of proteins called immunoglobulins. And we covered this a little bit in the blood chapter when we were discussing plasma. They are going to interact very specifically. It's very important that you know this is a specific interaction with just the epitope of an antigen. And these guys are secreted by plasma cells that are due to proliferating B lymphocytes. So, all immunoglobulins have a few things in common. One, they're going to have two identical light chains and two identical heavy chains. These are going to be bound together by disulfide bonds. So what that means is you'll have a amino acid with the sulfur group, another amino acid with the sulfur group, and these two will bind together to produce a sulfur-sulfur bond. Now, within the immunoglobulin, you also have an FC region. FC, the C is going to stand for constant in this case. So it's the carboxyl terminal end. So when you look at your amino acids and your proteins, you have a carboxyl end, your protein, and then an N-terminal end. This is where your nitrogen is, and this is where your carboxyl group is. So on the carboxyl end is where the Fc region is going to be, and this is how it's able to be recognized by cell surface receptors on your basophils and a few other cells. So in addition to the Fc region, you have the most important, which is the variable region. This is the area that's actually going to recognize your epitopes. So the first 110 amino acids near the amino terminal is going to be where this is. And it's going to vary, this should be very, sorry, widely among different antibody molecules, because this is how they're recognizing specific epitopes. So one heavy and one light chain of the variable region is going to be the antigen binding spot. And each antibody has 2 binding sites, which you'll see in the picture. So here is our kind of simplified artist rendition of a antibody. So we have our Fc region, so this is all constant. You have your heavy chain, and it's heavy because it's much larger. Our light chain, which is a little bit shorter. The constant region, which is the rest of the Fc, which is going to include part of your arm chain. And then you have the variable region. And then within that, you'll have your antigen binding site. And remember, there's going to be 2 for each one. And then your disulfide bonds. So get acquainted with this figure, because on the exam, you will have to either draw and label or just label a picture of an antibody. So there's 5 major classes of antibodies, the first being IgG. This is going to be monomeric, which means there's only one antibody. So when you look at an IgG, you'll have this, only one. It's the most abundant class, with about 75 to 85% found in your blood, very soluble and stable, which is important, and it crosses the placenta barrier. So what this does is when a mother gives birth to a newborn, that newborn has what we call passive immunity, which is a little bit of immunity to foreign invaders until their adaptive immunity is able to catch up. Because when they're in the womb, they're not being exposed to all these foreign objects like we are as when we're out. So it's very important that they get some sort of immunity once they're born to help prevent any sort of disease first out. The next one is IgA. This is primarily in exocrine secretions. So think of your tears, your respiratory tract, reproductive tracts, all these are going to release this. And it's in a dimeric form. So what that means is you now have, and I'm kind of simplifying the drawings now, 2 antibodies bound together, like that. And what's binding it together is what we call the J chain. Now these are produced by plasma cells in those areas, and it includes a secretory component, so that once it's released by epithelial cells, it's going to undergo transcytosis. So remember, if you have a group of epithelial cells, transcytosis means it's going to go through the cell and out the other side. And it's also going to assist in making it resistant to any sort of proteolysis and react with any microorganisms in those areas. The next one is IgM. This is pentameric. So there's going to be 5 antibodies all bound together by that J chain. It's going to be about 5 to 10% in blood, and it's the first to respond to an antigen. This is the most effective class in activating the complement system. So that's what the important part of IgM is. IgE is a monomer. So only one part, just like IgG, but the difference is the Fc portion is bound to either a mast cell or a basophil. So it's actually bound to a leukocyte, and this is how it's going to recognize antigens and activate these cells. Once your mast cells and basophils are activated, it's going to cause histamine, heparin, and leukotrienes to be released, which is going to cause your allergic reaction. And the last one's IgD. This is the least abundant in your body. It's a monomer as well. and it's going to be bound to your B lymphocytes primarily as your antigen receptors, and it's going to trigger B cell activation. So, why are all these antibodies important? What do they do? Well, first off, the actions of antibodies are to bind to an antigen, of course, at their antigen binding site, and it has to be specific, and then it's going to undergo one of these three functions. Either it's going to neutralize it, agglutinate it, which means it's basically going to clump them all together, or precipitate it out of the solution. So here's our neutralization. It's going to bind to the virus. If they're bound to the virus is not able to bind to your cells and infect the cells. Agglutination is going to form a clump by cross-linking them, and this is going to allow for your cells to more easily phagocytose them. And then precipitation, mainly with particles and toxins, are going to cause it to be insoluble anymore, and it's much easier to get rid of. So, your FC regions can bind to more things to cause even more functions of your antibodies. That was just the antigen binding site causing those three. The other ones are going to cause complement activation, which is going to be IgG or IgM, primarily IgM. And it's about 20 plasma proteins of the complement system in general. And the complement are going to bind to that, rupture membranes of any invading cells, and clump them together so that the leukocytes can come in and get rid of them. Opsonization is just another word for phagocytosis and increasing the efficiency of it. So what this does is if your antibodies bind to the bacteria, the macrophages are able to have a better grip. So when they grab onto the antibodies, they're able to pull it in much easier. And this is especially important if the bacteria has any sort of capsule around it, which makes it slipping to the macrophage. And then we have NK cells activation. This is going to activate our natural killer cells and going to cause the cells to release perforin and granzymes, which are going to cause apoptosis of the cells that are infected. So here's our complement binding. It's going to cause this to be ruptured. Here's our opsonization, how it grabs on, and it's able to pull that cell into it and phagocytose it. And then here's our natural killer cell releasing those perforin and granzymes to cause our cell, which is infected, to undergo apoptosis. So antigen presentation is done through by one protein that has two classes. So major histocompatibility complex, MHC. This is very important for immunology. There's class 1 and class 2, and it's involved in the immune rejection of grafted tissue or organs. So whenever people are like, well, are you compatible with someone to give a kidney or any other organ, this is what they're talking about, is the MHC class 1 and 2. So MHC class 1 will bind a wide variety of proteasome-derived peptide fragments. So what this means is, as your cells are making proteins, they're going to break a few of these up, put it on the surface of the cell, and say, hey, look, this is what I'm making. Is this normal? So if the T cell sees it, it's going to be like, oh, yeah, this is fine. This is just alcohol dehydrogenase. You're good to go. But if it's something more like reverse transcriptase for viruses, the T cell is going to be like, hold on, wait a second. This is not something you should be making. We need to figure out what's going on. MHC class 2 are proteins that are synthesized and transported to the cell, but only part of the mononuclear phagocyte system, your APCs. And this is going to allow these cells to go around and go, hey, look what I found. Is this normal? I found it floating around. And this will also signal T lymphocytes and activate the response if this is foreign. So the cells of the actual adaptive immune system are kind of a few of them. They are primarily your macrophages and dendritic cells of your APCs, and these guys are going to be what actually present the antigens to see if these are foreign. So the key things about antigen presenting cells is they're going to have a very active endocytotic system, and they're going to be expressing MHC class II. So inflammation is going to cause the release of interferon gamma, which is going to induce MHC class II in very specialized cells. These are what we call non-professional APCs. And these are going to be your fibroblasts and a few of your vascular endothelial cells. Now, lymphocytes are going to be regulating and carrying out your adaptive immunity. And remember, these are going to initially form in the bone marrow. And then once they become mature, or when they're becoming mature, they're going to occur in two different primary lymphoid organs. The bone marrow, which is where the B lymphocytes come from, and the thymus, which is where T lymphocytes come from. Once they're mature, they migrate to our secondary lymphoid organs, which is going to include our MALT. And there they're going to recirculate through the body and connective tissues, blood, lymph, and just kind of look around for anything foreign. Now, generally, your actual appearance of lymphoid organs are going to change from day to day because the lymphocytes don't stay in one area all the time, so they're constantly moving. So the percentages will stay the same, but they're going to change what's in there each time. Generally, the lymphoid tissue is going to be reticular connective tissue, and it's going to be filled with lymphocytes. And these can either be diffuse within the connective tissue or encapsulated to form lymphoid organs. So remember, here's our secondary structures. So that's what we're going to be talking about with that. Now, lymphoid tissue is going to be packed with lymphocytes, and they're going to stain dark blue with H&E. Now remember, a lymphocyte looks like a cell with a very large nucleus and very little cytoplasm. So that nucleus is what's going to cause it to stain very dark. Now, secondary lymphoid tissue is supported by reticulum fiber network, and it's primarily type 3 collagen. So the fibers that are produced by fibroblastic reticular cells, and they're going to be easily identified when you stain them. So here's our secondary lymphoid organ, and you can see the nice little framework of reticular fibers, which are collagen type 3, and they're going to be quite easy to kind of see. This is going to be a silver stain, because remember, type 3 is agriophilic. And here's an H&E stain of the lymphoid tissue, and you can see that in this area it's very dark purple due to all the nuclei. All lymphocytes are indistinguishable using light or electron microscopy. You can't tell if it's a B or a T cell unless you use some sort of method to determine the CD marker. And we'll get into that in a second. Now, this can be either flow cytometry or immunohistochemical methods. Now, the receptors on your B and T cells have immunoglobulins as well. They're going to bind to the antigens directly. So if you remember, the IgD is found in the B lymphocytes, just as an example. The T cell receptors only react with antigens that are bound on MHC molecules. So this is going to require additional proteins, CD4 and CD8, which are your CD markers. So here's our T cell, here's our CD4, and our CD8. And then you have your T cell receptors. A B cell is only going to have the B cell receptor, which is basically IgD. So T lymphocytes are long-lived, and they are the primary type of circulating lymphocytes, about 75% of them. They recognize antigen epitopes via surface protein complexes, which are your T cell receptors, which are made up of two glycoproteins alpha and beta chains, and they have a variable region very similar to your antibodies. These are only going to react with antigen epitopes in the MHC, so we call these MHC restricted. Now within our T cell population, there's different types of T cells that each have their own function. The first being helper T cells. We also call these T8 cells. These are characterized by CD4, which means they're going to bind to MHC class II. These are going to assist in the immune response by producing cytokines, which is going to cause differentiation of B cells into plasma cells, activate macrophages, activate cytotoxic lymphocyte, T lymphocytes, and induce other parts of the inflammatory reaction. After the infection goes away, some of these are going to remain as memory helper T cells. So here's our helper T cell. He's hanging out. He binds to one of our APC cells, so they're going to have an MHC class II. It's going to bind to the CD4 and T cell receptor and cause interleukins to be released, which is first going to stimulate our cytotoxic T cell, and it's also going to cause B cell proliferation, and eventually these T cells are going to proliferate and eventually form memory helper T cells. So CTLs are our cytotoxic T lymphocytes, and these guys are CD8. So what that means is our T cell receptor is going to have a CD8 portion to it, and it's going to bind MHC class I molecules. So if interleukin 2 is present due to our T helper cells, the CTLs are going to recognize the antigen and activate and proliferate. IL-2 comes from helper T cells, and the cytotoxic T cells are called killer T cells at this point, once they activate. They attach to the cell surface and remove the antigens and release perforins and granzymes, which are going to cause apoptosis again. This is our cell-mediated immunity, very similar to our NK cells, if you remember. And once these guys are activated, some of them stay on as memory cytotoxic T cells. So here's our cytotoxic T lymphocyte. It's going to bind CD8 MHC class I molecule. And if interleukin 2 is present, we're going to cause granzymes and perforin to be released, which will cause apoptosis of our cell. And then we'll have a few that are going to differentiate and eventually form memory CT cells. The next one is the regulatory T cell. We call these Tregs or suppressor T cells. These guys are going to have CD4 and CD25. Now don't get confused, because if you have a CD4 cell, this can be either a regulatory or a T helper. It depends on if CD25 is present. These are going to inhibit immune responses of the cell, and these are identified by the presence of FOXP3. FOXP3 is just a transcription factor that's going to allow for immune tolerance and maintain unresponsiveness to self-antigens. So this is important because you don't want your immune system to start attacking all your cells. If they're not infected, we don't want them to die. So this kind of suppresses it and prevents an excessive immune response to any sort of antigen. So these guys are important for what we call peripheral tolerance. And we'll get into central tolerance in a little bit, but it just kind of helps with keeping your T cells in check. The last ones are gamma delta T cells. These are a very small population. They're going to contain gamma delta chains instead of alpha beta. These are going to migrate to the epidermis and mucosal epithelial and become part of the intraepithelial and really don't recirculate once they get there. And these guys are more in the innate immunity. So these guys are interesting because they're part of the innate immunity, but they're a cell of the adaptive immunity. So then we go into B lymphocytes. Remember, these are monomers of IgM or IgG, and these are B cell receptors. Once the B cell receptors bind an antigen, they can bind them either if they're free in the solution, exposed part of an infectious agent, or already bound to antibodies. So the antigen receptor complex then undergoes endocytosis of the B cell. This is going to be degraded in the endosomes. Peptides from the antigen are presented on MHC class II molecules of the B cell, and then the helper T cell will then bind to that molecule, or the B cell, and activate it through cytokines. These are going to induce recombination in the immunoglobulin genes and stimulate several cycles of cell proliferation. Recombination is what gives us our variable region of our antibody. So here's our B lymphocyte, naive, just hanging out, binds to an antigen. A T lymphocyte will bind to that MHC class II, release interleukin 4, which will activate it, form either memory lymphocytes or plasma cells, which are going to be releasing our antibodies. So, in secondary lymphoid tissue, B cells are going to interact with follicular dendritic cells, or FDCs. These are going to have long processes, mesenchymal in origin, and they're going to not have that MHC class II molecule, but rather they're going to have antibody-antigen complexes bound to their receptors for complement proteins. So B cells attached to these become activated and aggregate as a small primary lymphoid nodule. The adjacent Th cells will assist, causing them to form a much larger, more prominent secondary lymphoid nodule. So they're going to stain lightly in the germinal center, which is where our lymphoblasts are, and they're going to undergo immunoglobulin gene recombination, proliferation, and quality control. And then once they're activated, they're going to cause the non-proliferating cells to be pushed to a darker area in the mantle. So the germinal area is where everything's occurring, the mantle is where things aren't occurring, and then after 2 to 3 weeks, it all goes away. So here's our secondary tissue with our large aggregates of our lymphocytes. This is our germinal center, a little bit lighter, same here. And here's our mantle, where the ones that aren't undergoing proliferation are, much darker. Most of your new lymphocytes will eventually become plasma cells. And these guys are going to secrete our antibodies that will bind the same epitope that the B cell recognized. B cells are what provide our humoral immunity. So once they do that, the newly B cells remain, or some of these will remain as memory B cells. So we're going to go into the thymus so that y'all understand central tolerance and how it comes about. The bilobe structure is going to be located in the mediastinum, so right in your chest area. The main function is central tolerance, and this is going to prevent autoimmunity. This is going to come from the endoderm during development of the fetus, and it's fully formed and functional at birth. It's going to be large and very active all the way until puberty, where it starts dying off. So here's our child's thymus, quite large compared to an adult's thymus, which becomes smaller. What happens is it fills with adipose, and there's a little bit more of your thymus active areas left, but most of it's going to be adipose tissue, whereas in the child there's not very much adipose at all. This whole process of becoming adipose tissue is called involution, where it decreases in size and activity. Now the thymus is divided into lobulars by vascularized connective tissue capsules. Each one has a cortex, which is going to be a darkly basophilic tissue surrounded by a medulla, which is going to stay a little bit lighter. The staining difference is going to be due to lymphoblasts and lymphocytes found in the cortex. So here's our medulla, much lighter than our cortex. And then here's our capsule. So the cortex is going to contain our T lymphoblasts called thymocytes, and these guys are going to be associated with thymic epithelial cells, or TECs. These have features of both epithelial and reticular cells. and they have a very large euchromatic nuclei. And additionally, there will be multiple macrophages in this area. The three major types of TECs of the cortex is the blood-thymus barrier. These are squamous TECs, and they're going to have occluding junctions to prevent cells from leaving. They're going to be the connective tissue of the capsule and septa and prevents any unregulated exposure of thymocytes to antigens. We don't want our thymocytes to be exposed until we're ready for them to be. Then we have our cytoreticulum. These are cells with processes containing keratin, tonofilaments, and desmosomes. The macrophages and developing lymphocytes are going to attach to these instead of reticulin fibers. The cells are considered APCs, and they express both MHC class 2 and class 1. We'll get into why they do that in a second. They secrete cytokines for T cell development in the thymus. Then we have our corticomedullary barrier cells. These are going to form a sheet-like structure between each lobule, and they're going to only express MHC class 2 proteins. So here is our thymus and our cortex, and the E is going to represent our epithelial cells. So you notice these are more squamous shaped compared to the others, and here's our nucleus, very euchromatic. So here's kind of a breakdown of it: our desmosome, our thymic epithelial cell, kind of circling around it with our lymphocytes on the inside. So there's three types of medullary TECs that are going to layer between the cortex and medulla, in addition to the corticomedullary boundary. So we have our cytoreticulum, which is going to support less densely packed T lymphocytes, dendritic cells, and macrophages, and these are going to express proteins specific to cells and other organs. Then we have Hassel corpuscles. These are large aggregates of TECs, and they're going to be concentrically arranged. This is unique to medulla, and they secrete cytokines to control the activity of the local dendritic cells and to promote development of regulatory T cells. So here is our medulla of our thymus, and the E cells are going to be our epithelial cells. So once again, our nice little squamous cell. Here's our Hassel corpuscle, and notice how it's kind of arranged and a bit different than what we saw in the cortex. So the medulla microvasculature is not going to be surrounded by a tight layer of TECs. So what this allows is once T lymphocytes get to here, they're able to exit the thymus. So the role of the thymus in T cell maturation selection is to make sure that we have central tolerance. So the thymus is the site of removal of T cells that are reactive against self-antigens. T lymphoblasts arrive in the thymus do not express CD4, CD8, or TCR. They're what we call naive, and they're just kind of still differentiating. Lymphoblasts begin to proliferate and recombine the variable regions of the TCR alpha and beta chains. And once they do that, they start expressing the TCR proteins with both CD4 and CD8. So once we get to this part, the thymocytes are in a very stringent two-stage selection process, and this is very important for the exam. This is important for quality control. They ensure that our T cells have TCRs that work, but they don't work against our own self-antigens. And it begins in the cortex and ends in the medulla, where they're able to exit into the circulatory system. So we have positive selection first. The cytoreticulum of the cortex, so we're starting in the cortex, present with peptides on both MHC class 1 and 2. This is important for development of both CD8 and CD4 T cells. Now this is going to determine if our proteins are functional at all. So basically, if your cells cannot bind to the MHC class 1 and 2, then they're not functional and they die. So up to 80% of these guys will undergo apoptosis and removed by the macrophages. The T cells that are normally binding to MCH class 1, where they're not binding too tight and they're able to bind, are then moved on to the medulla. So here's our T cells. We have CD4 and CD8, so it's kind of a mixture of both. And then we have our cortical epithelial cells with both MHC class 2 and MHC class 1. If it binds, good, they get to survive. If they don't bind, they die. And this is about 80%. Then we go into negative selection. This is going to occur in the medulla, where they encounter antigens presented by cytoreticular T cells and dendritic cells. The focus is to make sure that these guys do not bind to self-antigens. So if they don't bind to MHC molecules with our own self-antigens, with these peptides, then we are good. If they bind too strongly, they undergo apoptosis. Now, these peptides that we'll find are tissue-specific antigens, meaning that they're from many different tissues in our body other than the thymus. If any T cell that binds strongly to our tissue-specific antigens are released, we have a very damaging autoimmune system response that will occur. So, here's our second stage, our negative selection. TCR, this is our pre-lymphocyte, going to have MHC class 1 and 2, CD4 and CD8, and MHC class 1 and 2 over here. They're going to bind. Does it recognize our self-antigen and binds strongly to it? Then yes, they're going to die. If no, they get to survive. So, once we get to this point, only 2% of our T cells that were sent to the thymus survive and get to pass both selections. Now, depending on which MHC class molecule they bound to the most determines which CD is no longer expressed. So if they bound to the MHC class 1 more than they did to the MHC class 2, then we are going to have a CD8 cell rather than CD4. So here's our 2%. They either lose one or the other. And then we have our naive immunocompetent T lymphocytes that are going to be released. This figure is very important for the exam, and I recommend kind of reviewing this quite a bit. This is the end of this lecture. Make sure y'all kind of watch this a few times. It will be on the exam, especially this last part and the immune system in general.